Hello, my name is Frank Noé. I'm from FU Berlin, and I will speak today about variational methods and deep learning for high-dimensional dynamical systems. And we are very interested in developing machine learning methods for physical problems. Now, if you consider AI or machine learning methods in general, there are some famous examples that I'm sure you'll know. So, for example, there are all of these control problems around building robots that maneuver in complex environments or do tricks such as this one. There is reinforcement learning used, for example, in the AlphaGo system of Google DeepMind to learn to play Go. And when we develop machine learning methods, then we always have to think about two things. So what is the goal? What's the learning goal? What's the optimization problem? So for example, is there something like a loss function that we can minimize, and what is that? And what is the learning structure? So what is the structure that holds the parameters, and what does this induce about our problem solution? What does it mean for our problem solution to have a certain structure? And in physics applications, we often have a lot of physics background which tells us something about these two choices. So what is the optimization problem? In many cases in physics, we do not have supervised learning where we are just trying to match given labels by minimizing some error of the label prediction. We often have unsupervised learning problems. And in many cases, we have deep physical statements about what is the quantity that we really want to optimize in order to solve a certain problem, such as a variational principle, for example. And same with the learning structure. So in many cases, we have certain requirements on a machine learning method that makes predictions for physical systems. We want certain properties. We want maybe certain symmetry, certain conservation laws, certain invariances to hold. And that means we should probably build that into our learning structure because that makes learning easier and it can avoid catastrophically wrong or simply stupid predictions. Now I will focus on molecular physics here, and I will specifically focus on the sampling problem and the kinetics of molecular simulations. That is all atom molecular simulations where we model how, for example, proteins behave. These are two small proteins, really small, and the simulation system with them is about 100,000 atoms large. We are interested in how these proteins find and bind each other, how long it takes to do that, how long it takes to dissociate again, how that would change if we make little changes to the protein, such as mutations, etc. And we can do simulations for that. We have simulation models, such as energy functions. So these are that's a long story where they come from, and they can also be machine learned. But let's say we somehow have an energy function that tells for every state of the system, so for every positioning of atoms in space, how happy the system is, how energetically happy the system is, and that will translate into a probability distribution that we want to eventually sample in the long run. But we also want to sample how it gets from state 1 to state 2, so dynamical information. So we want both. Okay, so how do we do this? We can simply do all atom molecular dynamics simulation of this system, which is basically some sort of diffusion in this energy landscape. And there are very efficient programs for this. And these very efficient programs, if we run them on GPU, a state-of-the-art GPU for 1 week with this system, we get about 1 microsecond of simulation data. 1 microsecond of simulation data. If we do that 50 times, so for 1 GPU year, we get a single binding event for this system. And that is still doable if we don't do it in one trajectory, but we parallelize it. But the dissociation, that's the big problem, because it takes 1 hour of real time to dissociate this system, and that would be 1 million GPU years, and that is simply completely infeasible. So this is the sort of problem that we are facing here. That's a so-called sampling problem, and we want to know what methods can be used, what can we do in order to beat the sampling problem and still compute quantities such as probabilities to be in bound, non-bound, such as transition rates from bound to non-bound, etc., without having to simulate 1 million GPU years.